interesting. So, next speaker, next presentation will be multifractal downscaling models, a crash test by Elena Volpi. It should be Federico Lombardo. This conference is only for brave, so I think it's
Okay. Good afternoon to everybody. First of all, I want to thank my co-authors, which are my colleague Federico Lombardo, Simon Papalexio, and Professor Demetris Koutsoyannis. So, this presentation is about the reliability of the multifractal analysis that it's at the basis of the identification and the fitting, the calibration of the multifractal rainfall downscaling models. These models are widely used in literature, are very popular since they are very parsimonious and easy to implement, and in particular they are able to reproduce several statistical properties of rainfall in a finite but practically relevant range of scales. And the most important property is the scaling of the moment of order Q with the scale of aggregation that we call F. However, when we want to estimate the moment of order Q, we can have some problems because the estimation of the Q-order moments can be very uncertain, particularly in the case the underlying process is characterized by a strong temporal dependence. So, conclusions from a multifractal analysis which is performed for a single time series can lead to misleading results sometimes. So, the aim of this topic is to understand, to analyze the uncertainty that characterize the sample estimates of the Q-order moments as a function of the statistical properties of the process, of the scale of aggregation, and of the order of the moment Q. So let R be a stochastic process, continuous in time, which is characterized by a mean, a variance, and an autocorrelation function. It describes clearly the time dependence. Usually we supposed to observe this process on a time window that we call T, and we observe the process at finite and straight scale that we call delta. When we perform the multifractal analysis, we used to aggregate the process in order to obtain a mean aggregated process, which we call RF at the scale F. And we used to compute the Q-order moments of this process, the mean aggregated process. So the multifractal analysis is based on detecting power law behaviors for the Q-order moments respect to the scale of aggregation F. And this power law relationship is characterized by an exponent function, the moment scaling exponent function, KQ, which is typically a nonlinear function of Q. So in the calibration of the multifractal model, we need to estimate the moment scaling exponent function, and we estimate this function on the basis on linear regression on a log-log diagram in which we represented the Q-order moment respect to the scale. Clearly, the first thing we have to do is to estimate the sample Q moments from this relation in which R is the mean aggregated process and N is the number of elements of the mean aggregated process, which depends on the scale of aggregation. These estimates can be characterized in terms of its expected value and of its variance. The expected values is always equal to the theoretical value, so the estimator is an unbiased estimator, while the variance can be assumed as a measure of the uncertainty that characterizes the moment estimation. And clearly the variance is expected to depend on the statistical properties of the process, on the aggregation scale F, on the sample size, and of the order of the moment. So the dependence of the variance of the coorder moment estimation on these properties of the process that we can observe can be clearly understood in the case of the moment of order 1, in the case of the mean. In the case of the mean, the variance can be expressed analytically by this relation, this well-known relation, in which we can see that the variance is independent. It's not depending on the scale of aggregation, while it still depends on the characteristic of the process, in particular on the autocorrelation function of the process, and on the length of the observed series. And in this picture, we have shown the behavior of this variance, which is normalized with respect to the variance of the process, for three types of processes. An independent process, a process which is characterized by an exponential autocorrelation function with a fixed integral scale, and a Harsh-Kolmogorov process with different values of the Harsh coefficient, so with different values of the time dependence. As we can see, the greater is the time dependence, so the greater is the Harsh coefficient, the greater is the length of the time series that we need in order to obtain estimates of a similar quality, of a similar accuracy. So it's clear from the analysis of the mean that the uncertainty of the mean in this case strongly depends on the length of the time windows as expected and on the Harsh coefficient, so on the temporal dependence of the process. We now want to investigate the behavior in terms of this uncertainty of the moment of higher order. And we investigate it through a Monte Carlo simulation, since we are not able to produce similar analytical results with respect to the case of the mean. In particular, since we have seen which is the role of the Harsh coefficient, so of the temporal dependence, and the role of the time window in determining this uncertainty, in particular, we focus on the effect of the scale of aggregation and on the order of the moment. So, to this aim, we use a stochastic model, which is based on a Monte Carlo approach, and on a Harsh-Kolmogorov process, to generate a large number of time series, which are characterized by a log normal distribution and by a fixed length, which is equal to about 1,000 elements, and with fixed value of the mean, of the standard deviation, and of the Harsh coefficient. Let's see some results. The first picture shows the behavior of the empirical cumulative distribution functions for the moment of order 2 ranging from 1 to 6, and for all the scales of aggregation that we have considered in the analysis. And the empirical distribution function are the distribution of the ratio among the moment of order Q and its theoretical value. So this distribution are spread around the theoretical value. And this is clear because the moment estimator are unbiased estimator. But we can know that the range of variability of the moment estimation is very large. Note that the plots are in a semi-logarithmic scale. And clearly the range of variability is larger in the case of high order moments. The situation slightly perform better in the case we aggregate the process. So if we pass from the finer scale to the coarser scale. Another important point can be observed when we plot the empirical density function of the moment. In particular, we see in the figure the empirical frequency distribution of the moment of order 5, in which we can see that there is, even if the estimator is unbiased, so even if the estimator, the distribution is centered around the 0, there is a strong difference between the mode of the distribution and the expected value. And this is important because when we perform a multifractal analysis, we used to perform it on a single series, so it's much probable to obtain a value which is similar to the mode than to the expected value. And this difference slightly reduces with the scale of aggregation. So this is a sort of summarizing figure in which we can observe the behavior of the moments of order Q for every aggregation scale. We can know that the variability of the moment estimates increases with the order of the moment. We can see that the difference, we can also know that the difference between the expected value and the mode of the empirical distribution of the moments increases with the order of the moment. Now, let's pass to the graph that represents the basis of the multifractal analysis. In the multifractal analysis, as I was saying before, we use to estimate the moments and the variability of the moments with the scale of aggregation, and to fit a linear regression in the log-log diagram. So in a diagram like this, in which we have the moment and the scale, we estimate the slope of the linear fitting, and this slope is a measure of the multifractal exponent that it's the characteristic of the multifractal process. So in our simulation, we can see that the uncertainty, which is related to the estimation of the different order moments, different moments of the different order, it's strongly variable with the order of the moment, and also it is not so strongly variable with the scale of aggregation. So as a consequence of this variability, of this uncertainty, which is variable across the order of the moment and across the scale of aggregation, we can observe that when we analyze a single series, when we perform a multifractal analysis of a single series, of a single time series, we can obtain misleading results. As an example, we have reported here the multifractal analysis of 2 of the 30,000 series that we have synthetically generated. And in the example, we can observe that even if the process that we have generated is not multifractal, we can observe a linear behavior of the moment with respect to the scale in the log-log diagram, and we can estimate a scaling exponent function which is nonlinear, increasing with the moment of the order Q, which is a sign of a multifractal process. So even if the process is not multifractal, due to the uncertainty in the estimation of the moments, we can, the analysis of a single series can lead to a multifractal sign. So, in conclusion, we have performed some numerical experiments with the aim of forming a sort of crash test of the multifractal analysis. And what we want to highlight is that we have to pay attention when we tend to calibrate the models on the basis of the estimation of the Q-order moments, because these moments are affected, the estimation of these moments are affected by a large uncertainty, which is variable across the scale of aggregation and across the order of the moments. And that's all. Thank you.
Comments for Elena? Elena, I have just a question. Do you use for the simulation series of 1000 2004 data length? The length of the data impact the estimation of the moments in some way of the highest order, or?
Yes, sure. The impact of the length of the data can be observed in the analysis of the behavior of the variance of the mean of the process. So it's the same for every order of the moment. Its behavior is similar for every order of the moment, and it's similar across the different values of the IAHS coefficients.
Okay. Felix.
Maybe my question is lateral for your presentation, but it's important for me and maybe for other people in the audience. In the previous presentation, we saw that there is 3 breaks in the fractal characteristic, and in my experience, we found the same things related with the duration of convective cells, storm duration, and synoptic situations. In your Monte Carlo simulation, did you find also this type of breaks, or everything was smooth? The whole range of
no, we didn't find it, but the Monte Carlo simulation are based on series which are synthetically generated using a model which reproduce the same pattern across the scales. So we cannot observe this break of scales that we observe in the natural processes.
Okay, I think we can move on with Martinus Thunderbird. Fitting asymmetric cobblers for rainfall downscaling. Very good.